Okay, let's try another problem here. We have two blocks, A and B, stacked on each other. A is stacked onto B. They sit on a surface with the coefficient of friction equal to 0.35. Up here, the coefficient of friction between the two blocks is 0.3, and this is actually a static coefficient of friction, whereas this down here is the kinetic coefficient of friction, because we're going to pull this block along here with force P. So we're going to find the largest force P we can get away with, but ensuring that block A does not slip. We can solve this problem purely with kinetics. Let's start with a free body diagram of A. And here we have the weight, which is 60 times 9.81. And we also have a normal in here pushing up, and friction. So the way you rationalize this direction of your frictional force is if the top block slides, then it's going to slide to the left relative to the right block. So friction is going to point to the right. Okay, well, this will set this equal to our kinetics diagram, and let's say we have mass times acceleration in the x direction. Okay, so let's sum forces here in the x, and this equals, actually let's do a quickie in the y direction just to demonstrate. So force in the y direction equals 60 times 9.81, and let's call this negative for the weight, and then we'll go positive with our normal force. Let's put an F here so we don't confuse that with newtons, and we don't have any acceleration in the y direction, so this equals 0. So our normal force then we see equals 9.81 times 60. Now we can sum forces in the x and use that value in our friction. So we'll have our coefficient of static friction, or of 0.3 times the normal force, 9.81 times 60, and that's it. And this will equal, or mass times our acceleration, which is 60 times our acceleration. We can solve for that as 2.943 meters per second squared. Now, so long as we don't exceed this value, we won't get slippage. So that means the maximum value for our acceleration in the combined problem is going to be 2.943. Drawing free body diagram for the combined problem now. We have a weight of 90 kilograms times 9.81, that's 30 plus 60. We're going to have friction here holding us back, and a normal force. So again, the normal force here is equal to our weight. So we can dispense with summation of forces in the y this time. But let's put our kinetics relationship in. Again, we have mass times acceleration. So if we sum forces in the x direction, we end up with P minus our force of friction, which is 90 times 9.81 times the coefficient of friction now is 0.35 for kinetic friction there, and this equals 90 times our acceleration. So we can now solve for P. So P equals 573.9 newtons. If we pull with a force higher than that, we will get slippage up above. Okay, let's work on this pulley problem now. In this problem, we want to find the velocity of B, I think, after 2 seconds. So we have a mismatch in weights here and a pulley system. We're going to find the velocity of B after 2 seconds. Okay, so let's come up with we have this single cable, which is green here, and we have this pulley system. Your intuition will probably tell you that the 50 kilograms is going to go down. So, and that means the 15 will go up. But we need to come up with a relationship that relates the lengths of these cables. And if you think about it, we can look at this distance, which is a delta B. Draw that a little better. And that means we don't really have to worry about this length out to here, because that's going to be constant, and so if we differentiate it, it'll disappear. So then we can compare that to this length that also changes, and that's we'll call that delta A, not delta B. So we can see that if we work out then that the length we're interested in is L equals 3 delta B plus a delta A. And when we differentiate that twice, essentially, we're going to end up with 0 because L is constant, 3 times the acceleration of B plus the acceleration of A. So the acceleration of A equals minus 3 times the acceleration of B. So let's investigate our blocks now. Start with the free body diagram, and we'll look at the kinetics of the situation. So we essentially have 3 T's on B and a weight. So these are 3 T's and a weight of 15 times 9.81, and that's going to be equal to, now what I'm going to do here is I'm going to draw this up, and I'm going to set my positives condition to up 2, and that's my mass times my acceleration. This is 15 times 9.8, or 15 times the acceleration. What am I saying? 15 times the acceleration at B. So let's write that out then. So we have T's are positive. We have 3 T's minus 15 times 9.81. This equals 15 times the acceleration of B. So with block A, I have 1 T. It's the same rope. It has to have the same tension in it, and a weight of 50 times 9.81 for my free body diagram. And then this will be set equal to, and again, I'm going to point this up even though I know it's not. And so this is the mass times the acceleration at A. And we'll call this 50 times A. So let's draw our equation of motion. So we've got T minus 50 times 9.81 equals 50 times the acceleration of A. Now, again, I'm going to call this positive. As long as I'm consistent in each equation, things will work out. What I mean by that is as long as I draw my forces consistently with this and set it up consistently in my equation, the relationships will all come out in the wash in the right direction. So this we can further modify because the acceleration at A, as we see above here, is equal to minus 3b. So let's put that in. Minus 3 acceleration of B. We got to make sure we are paying attention to our signs. Okay, I have two equations and two unknowns in this. So I can solve this for T and for the acceleration of B. So T equals 63.29 newtons, and the acceleration of B equals 2.84 meters per second squared. Notice this is positive, so it is in the positive direction. I'll just draw an arrow there. I can also calculate what the acceleration of A is, although I won't need it for this problem, using that length description I have up above, and it equals minus 3 times this, which is 8.554 meters per second squared. Now it actually is negative because it's minus 3 times that, so that means that this is really 8.554 accelerating down, just as our intuition told us. So now we have a constant acceleration down. We want to figure out what our relationship, our velocity is in that direction. We could say that AB equals the integral of dv dt. So what was it, 2.84 meters per second squared times the integral dt from 0 to t. And then t here was set to 2 seconds. Did I state that in my problem? So t equals 2 seconds, and I did state that in the problem. All right, and then that equals the integral of dv from 0 to v. So 2.84 times 2 equals the velocity. So this was 0 because we had an initial velocity of 0 up here. And this equals 5.696 meters per second. It's positive, which means we are heading up. And that's it.